Did you even say hi to him? He was talking to us.
All right, it's 5:30. Let's go and get started. All right, sorry class, I'm still getting ready a little bit. All right, how's everyone doing today? Good, good. All right, let me just, it's too late to write learning objectives. So I'm gonna just write the title of the lecture today. Okay. Shell and beam elements, all right. Okay, all right, so we're going to go and talk about something today. Just like we normally do, we talk about something. Oh man, I'm discovering that as I get older and older and I get less and less sleep, I get worse and worse at stalling for time. All right. So the plan for today is that we're going to talk about shell and beam elements. And so, last week, we kind of spent the entire week talking about what I call all the solid elements. And so that's the tetrahedrons, hexahedrons, talk about element order and all that stuff. Today, we're going to talk about special elements, and we're going to implement that in the activity on Thursday. Okay? So this is an ANSYS week, and so it's an odd number week. So we have ANSYS activity 4 coming up on Thursday. That's going to be an application for this right here. Okay, and so of course this is, and I think this is going to be the last ANSYS activity that we'll do actually for a while, because I know you guys have the project out right now, and so I didn't want to overload you guys too much. But I did want to cover this before we did the project, because depending on which project geometry that you choose, you can actually implement some of this into your project. And so actually a lot of people did that last year, and it was pretty cool. And I actually didn't expect it, but they were able to get some cool results with shell and beam elements. Okay. All right, and so announcements. And so I know that activity 3 was due yesterday, and so I'll try to grade those as soon as possible, just so that you can have that grade. All right, and so are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started with shell and beam elements. Okay. All right. And so up to this point, we've been using elements in ANSYS, and we spent a fair bit of time talking about them. But I would consider all of those to be of the same type of element called solid elements. Okay. Okay. And so I call them, and so they're often called solid elements because they're solid. They are solid, they're reliable, so we say, they're solid elements, but they also take up a 3-dimensional amount of space. And so, from here on out, I'm just going to make the assumption that we're going to be working in 3D. Okay. And so the solid elements in 3D, of course, are tetrahedrons. And our hexahedrons. Okay. And so, we talked about, their differences last week, but they do share one thing in common, in that both tetrahedron and hexahedron are three-dimensional shapes. Okay. Right? And so that's good most of the time. So, most of the time we're going to be meshing and working with 3-dimensional solids. And so, we want 3-dimensional elements to mesh that solid. Okay. But there are certain cases where, we actually don't want to use, or it's preferable not to use solid elements. Okay. And those cases are situations when our geometry itself doesn't look like a fully three-dimensional object, right? And so that sounds like kind of a weird paradox, but I'll kind of explain that in a second. And so when I say it doesn't look 3D, what I mean is that we can sometimes we can better represent it as either a 2D or even a 1D structure. Okay. And so what cases come to mind for that? Those are cases when your geometry is either very, very thin or very, very slender. Okay. Okay. So let's draw a couple examples. So let's say that we're doing a finite element simulation, very thin plate. So this happens a lot in practice. And so if you want to do a simulation on a part that's very thin, what you'll see is that the solid elements will actually have a hard time, first of all, meshing it, and second of all, getting accurate results on it. Okay. That's one example. Another example could be, if you have a very, very slender element. So, it's not very uncommon to see a structure made up of thin rods. Okay. And so those rods or those beams, are very slender. Okay. Okay. So thin and slender are kind of I'd say the conversational terms that we use to describe these, but we can do a bit better. Okay. And so when I say something's thin, that means that one dimension of the geometry is much smaller than the other two. And so in this case, we have the thickness of this plate. Okay. If we compare that to the width of the plate into the page and the width of the plate, parallel to the plate page. Oh, man, I need to sleep more. The thickness is a lot smaller than those two. Okay. And so, that's what we consider to be thin. And so for the slender beam, we consider a geometry slender when one dimension is much, much, larger than the other. Yeah, Roman, I see your question. Let me write this up first. Okay. All right, so question in the chat. All right, so question in the chat is, what is the definition of much smaller? Is there a ratio? No, that's a great question, because even these definitions have leave a lot to interpretation. Okay, and so when I say much smaller or much larger, usually the threshold that I use is about 1 to 10. And so if you have one dimension that's about a tenth of the size of the other two, that's what I consider to be really, really thin. But but some other people have different opinions on what's considered to be thin and what's considered to be slender. And so I've talked to people where they consider 1 to 8 being a thin. Some other people might consider 1 to 5 very, very thin. For me, I do 1 to 10, but that's just kind of based on my own experience, and it's going to depend on your application as well. Okay. All right. And so what these geometries have in common is that if you were to try to mesh these with a traditional solid element, so a tetrahedron or a hexahedron, you might run into some issues. And those issues either being, you might it might not be able to mesh unless you use an absurdly small element size. And even if you do mesh it, you might get results that they're not reliable. Okay. And so for these kind of situations, we say that, instead of trying to use the solid elements, let's try to use a more specialized element type that's more suited to these geometries. Okay. Okay. And so that's what shell and beam elements are going to do. Any questions on this? All right, and so what exactly are shell and beam elements? Okay, so let's talk about that now. And let's compare them to the solid elements. Okay. All right. And so at their core, shell and beam elements, they look like a lower dimensional element. Okay. And so a shell element is essentially going to be a 2D element. And a beam element is essentially going to be a 1D element. What is a 1D element, you ask? And so 1D element, let's look at a typical 1D geometry. And so the only 1D geometry that's available is a line, okay? And so 1D element is just a smaller line. So, we kind of break this up into, different line segments. Those are 1D elements. And so 1D elements are just, little line segments. And that's exactly what they look like in ANSYS as well. Okay. Okay. And so, you may be asking, what's so special about shells and beams? So we've already covered 2D elements. And 1D element is just a line segment. And so, what's so special about these? Okay. And so what's special, and so there's a couple of things that make them kind of special. And so, you might be thinking, a shell element is, no different than what we did for activity 1. And so activity 1, we did a fully 2D, simulation on a 2D plate. Okay. And so it goes a bit beyond that. And so a shell element is a 2D element, but it's simulating a behavior in 3D space. Okay. And so that means that, when you compute the deformations on a shell element and a beam element, you're computing all 3 components of the deformation. So it's going to be X, Y, and Z deformation. Okay. Okay. If you kind of remember what we did for activity 1, our activity 1, we used 2D elements, but that simulation itself was completely 2D. And so the deformation that we computed in activity 1, you can go back and check your files for this too. we actually only computed two components of deformation. So we only computed X and Y. We didn't compute Z. And so what makes shell and beam elements different is that we are actually going to compute X, Y, and Z deformation. Okay. So let me call that dx, dy, and dz. Okay. And so in that sense, the shell and beam elements, the amount of things that they're computing is the same as solid elements, because and for the solid elements, tetrahedrons and hexahedrons, we talked about that the first thing that they compute are the deformations, right? And so they compute all three components of deformation for solid elements, okay? Shell and beam elements actually compute a few more things. And so what they compute is actually even more than the solid elements, okay? And so in addition to that, the shell and beam elements are also going to compute the rotational degrees of freedom. Okay. And so I'll call those Rx, Ry, Rz. Okay. And so you might be asking, what are the rotational degrees of freedom? Well, if you have a beam like this, okay, and if you remember anything from beam theory from 331, okay, or wherever you learn it, okay, we know that when we solve our beam equations, okay, we get the displacement of the beam. And so that displacement is basically the same as deformation. But then we can also compute how much the beam itself is tilting, right? And so we can compute, what the angle of rotation of the beam is at that location. And so that's what I mean by the rotational degrees of freedom. And so, when we use shell and beam elements, we're able to compute how much that element is actually rotating, or how much its orientation is changing, in addition to how much it's deforming. Okay. And so in total, compared to the solid elements, the shell and beam elements compute twice as many degrees of freedom. Okay. And so it's twice as many degrees of freedom compared to solid elements, but they kind of need to. And the reason they need to is because the elements themselves are not three-dimensional objects. And so to kind of make sure that they can interact in three-dimensional space with three-dimensional objects, we have to compute these additional degrees of freedom to make sure that they can interact. Okay. Any questions on this so far? All right. And so, you may be asking, why why is it that we want to use shell and beams when it seems like we have to do kind of twice the amount of work, right? And so if the amount of things that we're computing per node is twice as many for shells and beams, then why are we even using them in the first place? And so, why don't we just use solid elements if we're going to do less work? Okay. Okay. And so remember, shells and beams are efficient whenever the geometry kind of allows them to do so. Okay. Okay. And so, shells and beams, they're going to be a lot more efficient for the thin and slender geometries. And what I mean by more efficient is that you get convergence on the solution. In other words, you get a more accurate solution with a lot less number of elements. Okay. So Roman, actually, this kind of goes back to the question you asked at the beginning. And so, you might be asking, how do you know you're going to get a more accurate solution with shells and beams? Right? And so we talked about, what are some of the ratios, what are some of the thresholds that you can use to consider something that's thin or slender. Here is kind of a really good tell. Okay. And so, let's say that you have a geometry. Okay. And so, of course, in this case, it's a fairly thin geometry. And so let's say that you're able to get a mesh on this. Okay? And so for just a thin rectangle like this, I wouldn't be surprised if you got a good hexahedral mesh on it. Okay. And so if we were to mesh this, let me use a different color here. Okay. And so let's say that we got a good hexahedral mesh. Okay. And so at first, you might be looking at this and say, hey, that looks pretty good. We have a good kind of mesh density on it. But I want to draw your attention to this area right here. Okay. In other words, I want you to kind of take a look at what kind of mesh density do we have going through the thin part of the structure. Okay. Because if we look at the mesh density in this direction and in this direction, in kind of the long directions, I'd say you have pretty good mesh density in those directions because you have kind of several elements that kind of go through that direction. Okay. But if we look at the thin direction here, we can see that we only have just one element through the thickness of this part. And so what this means is that if you only have one element through the thickness, that means you have no nodes on the interior through that part. Okay. Okay. And this goes for both tetrahedrons and hexahedrons. So if you have a situation where you're meshing with either tets or hexes, and you see an element that kind of spans the entire thickness, and so it goes from one end of the geometry to the other, that's usually a pretty big warning sign to me that maybe you should use, you can either use much smaller elements, or maybe you should switch up the element types here and consider maybe a shell or a bead. Okay, because what can happen here, and so having a situation like this, it's not the end of the world. You still be able to get a simulation through on this, but there are certain results here that are not going to be very reliable. The main result here is going to be the stress. Oh, I read your mind. Yeah, because remember, what we talked about last Thursday is that when you compute stress, you're basically computing differences in the deformation. Okay, and so if you're doing this without any interior nodes, you're basically computing the difference in deformation on kind of one exterior surface to another exterior surface, and so that's usually not going to give you a very accurate or reliable computation for the stress. Okay. And so stress is always a lot more reliable when you have a decent amount of interior nodes. Okay, but there are certain times when you just can't get it. Okay, and so you can try to get interior nodes here, of course. And so one way that you can fix this is just to refine the shit out of it. So you can basically just keep making the elements smaller and smaller until you get multiple elements through the thickness. Okay. Okay. So that's kind of a brute force way to take care of it. And so you just keep making the elements smaller and smaller. But you kind of sacrifice a lot of cost for that. And so by making the elements smaller in this direction, you also make them a lot smaller in this direction as well. Okay. And then very quickly, your nice little mesh that was maybe only a few, maybe 20,000 elements big, suddenly you're at 20 million elements, and you have kind of no idea what to do. And so it starts to become a problem. And so, that's why, kind of the way that you should think about shells and beams is that it makes situations like this a lot more efficient. Okay. It is possible to mesh this with solid elements. It's just that you're gonna make your computer cry trying to do that. And so what makes shells and beams so much better, right? And so in theory, shells and beams are, instead of a three-dimensional thin solid here, you would replace it with, a 2D sheet, right? And so this would be this exact same geometry, but with shells. Okay. Right. So you may be asking, what's the difference, right? And so, I mean, visually, it looks better. And so we replace the thin geometry with a 2D object. Okay. But how does this actually help us with our stress calculation? Okay. Remember what I mentioned earlier, that shells and beams, on a per node basis, we're computing additional degrees of freedom, right? And so for each of the nodes here, each node, in addition to the X, Y, and Z deformation, we're also computing the X, Y, and Z rotational degrees of freedom as well. the benefit that we get is that we can actually use these rotations to help us compute the stress, right? And so the stress calculation that we get from shells and beams not only depend on the deformation, but they also depend on the rotations as well. Okay. And so, yes, it's true that for shell elements, we are computing more per node. But those additional degrees of freedom that we're computing per node, we actually get a ton of benefit out of them because they allow us to compute things like stress with a lot more accuracy. Okay. And the other benefit that you get is that with shell elements, you don't have to really kill it with elements. So you can kind of mesh this in a lot more of an efficient way because you don't have to refine it so much. Okay? And so almost always, when you're comparing a solid element mesh to one that has shells or beams, the shell and beam mesh will have a lot more elements, or a lot less elements, excuse me. And so that by itself, will give you a lot of cost savings. And then also on a per element basis, each element itself will have a lot less nodes. Okay. And so we saw this last Thursday, right? And so if we compare, the quadratic quadrilateral, okay. If you count the number of nodes in this quadratic quadrilateral, you can see here that there's 8 of them. Versus its 3D cousin, the quadratic hexahedral. I don't even want to draw all the nodes because it's so many. I think that's all of them. Okay. And so the quadratic hex, we know, has 20 nodes. Okay. And so that's 12 less nodes per element. And so even though we're computing more per node here, right? And so we know that for a shell element, we're computing 6 degrees of freedom per node. That's the XYZ deformations and the XYZ rotations. And so per element, you can see that there's a total number of 48 degrees of freedom. We compare that to the quadratic hex. In the quadratic hex, we're only computing 3 degrees of freedom per node. Okay. And so we do the multiplication. So we see that, for the quadratic hex, we're basically computing 60 different quantities, right? 60 different deformation values for the quadratic hex versus the quadratic shell or the quadratic quadrilateral. Even with the rotational degrees of freedom, we only end up with 48 degrees of freedom per node, per element, excuse me. And so if you combine all these facts together, the fact that you can mesh it with a lot less elements per element, you have a lot less nodes. You're going to reach convergence a lot faster with less elements. It all kind of adds up to the same conclusion that if you have a situation where you can use shells or beams, use them because they're going to end up saving you a lot of cost, and you're going to end up with a much higher quality solution. Okay. Any questions on this? Right, and so again, what you're looking out for, what you're looking out for when you're trying to determine if you should use shells or beams are situations like this. And so if you try to mesh it first with a solid element and you see that you only have one element through the thickness, then that's kind of the indicator. And so once you kind of see that, then you're like, okay, I only have one element through this thickness. Maybe I should consider using a shell or a beam element. Okay. And so that's, a bit on the background of, what shell and beam elements are and kind of what's happening underneath the hood. Let's talk more kind of practical stuff. So let's talk about, how do you actually form these? And so what's kind of the typical way to actually make these in ANSYS, as well as some other stuff. Okay, so we'll start with shells. And so a shell element is basically a 2D element. Okay, and so it's basically comprised of triangles and quadrilaterals. So we talked about that quite a bit. And the assumption here is that these are acting in three-dimensional space, and so they have a relatively small thickness. Okay? And so that thickness, the thickness of the shell elements is not represented geometrically, right? And so you don't actually see the thickness in the 3D model, okay? And so instead, that thickness is stored as a property, okay? And so it's basically the same thing as like a density or Young's modulus, okay? Okay. Right, and so if you think back to some of our previous ANSYS activities, we've actually worked with shell elements in the last activity. And so if you remember, there was that application surface where you had to apply the wind force, right? Remember, one of the steps that we did in that activity was we assigned a thickness, okay? And the way that we did that was we just entered the number, or we entered the value for the thickness into it, some data box, okay? That wasn't exactly a shell element because that surface was just a dummy surface, but it was implemented as one, and so that's why we had to specify the thickness. We didn't actually do anything with that thickness, and that application surface didn't have any structural strength, but that's the idea. Okay? And so whenever you have a shell element, you have to kind of specify what that thickness is, before you use it. Right. So now let's talk about, how do we actually create shell elements in FEM? Okay. So there's four kind of general methods, and of these, some are more common than the others, but I thought I'd mention all four of them just for completeness. Okay. Okay. And so the first way to make a shell is to create a 2D sketch. And so you're going to make basically a sketch in 2D, and then you're going to tell ANSYS that this sketch here is going to be a shell. Okay. Another way to create a shell surface is to create just what I call an open sketch. Okay, and so that's just basically a line, and then from there you can extrude it into a 2D surface. Okay, and so as an example here, let's say that we want to create, let's say that we created a line that looks like this. Okay, and so maybe we created a sketch in either Design Modeler or SolidWorks, and we created a sketch like that. Okay. Then what we can do is we can say that, okay, here is our profile for our shell element. Now it's kind of extruded into the third dimension. Okay. So that's number two. Number three is the method we're going to be using on Thursday, and I think this is probably the most common because again, the most common way that FEAs use is that you create a CAD model in some other software like SolidWorks, and then you import it into ANSYS. Okay? And so number three will work with an existing CAD model, and so you don't have to build up the shells by scratch, which you kind of have to do for steps 1 and 2. Okay? And so in method 3, we use a tool known as a mid-surface. And so here's kind of an illustration of how that works. Okay. And so let's say that you have a CAD file. And then inside that CAD file, you have a kind of a relatively thin part of the geometry. And so let's say that you have a part of your CAD file that looks like this. Okay. And so in this case, it's relatively thin, and you want to replace this with a with a shell. Okay. And so the way the mid surface works is that you're going to select two parallel surfaces. Okay, so let's say this is surface 2, and on the other side surface is surface 1. Okay. And so the idea is that if you do have a thin geometry, in your CAD file, you're going to have two surfaces that are going to be, parallel to each other, so they're not going to touch, and they're going to be very close. Okay. And so the mid-surface operation, what you're going to do is you're going to select both of these, and then after you do that, and what ANSYS is going to do is that, okay, you said here are your two surfaces. Let me go ahead and make a shell that goes right in between these two. Okay. And so, if we kind of trace out the previous geometry, and so the previous geometry, would be basically eliminated, and then in its place will be a shell that's right in between the two surfaces that you selected. Okay. Okay. And so of course, this method is common because, again, you don't have to create your geometry from the ground up. Okay? And so if you were to use methods 1 and 2, you would create the CAD model with the intention of turning it into a shell. Okay. And so it kind of has a shell already built in just from scratch. But a lot of times you don't have situations like that because if you work at an engineering company, any kind of design firm, the CAD model is used for a lot more than just the FEA. So the FEA is just kind of one part of the whole design process. And so your CAD engineer is not going to, remake his entire geometry just so that you have shells and beams in certain parts. Okay. And so the fact that this exists, the fact that you can take an existing CAD with all three-dimensional parts and then kind of extract out the shells in certain areas is very appealing. And that's why this method is used the most. Okay. And so we'll be doing this a lot in the activity on Thursday. All right, any questions on this? All right, so let's talk about the last way to create a shell. So the last way to create a shell is to use a tool called a thin surface. Okay. Okay. And so the way the last method works is that you're going to start with a solid object, so very similar to method 3. Okay. except you're gonna, instead of kind of creating a surface kind of in between, what we're saying is I just want the exterior of this to be just kind of a thin shell. Okay. And so the way I like to think about this is when I was little, I think it still exists. I just haven't seen it in a while. You can get this like special chocolate syrup that if you pour it on top of your ice cream, it kind of freezes into a shell. And then you take the ice cream out and then you just have that kind of thin shell. This is exactly the same thing. And so imagine kind of pouring like a paint or some kind of chocolate sauce over your part. And then what you extract from it is just the shell of that. And you kind of get rid of all of the interior. Okay. There's a more gross analogy, and so you can think of it as like a bug shedding its exoskeleton and they're just stuck with the skin. A little bit more gross, but I like the chocolate one a bit better. And so unfortunately, this is really hard to draw because if I draw like a cube like this, and then I say extract the surface, then it's just going to be the same cube, but now it's hollow on the inside. Okay, so it's hard to draw. So I think it's a lot easier to kind of explain it in words. Okay. Yeah, I know it's dinner time. I'm hungry too. Okay, so those are the main methods, and so four is kind of a neat trick, but I would say it's not used all that commonly, although it certainly does have its uses, and so method 3 definitely gets the most use out of the 4. Okay. Any questions on these methods on how to make shells? All right, so we'll get plenty of practice with this on Thursday. Okay. All right, so now let's talk about beam elements. All right, and so let's define it first. And so once again, a beam element is a one-dimensional element that's used to represent a slender geometry. And so, compared to shells, beams are, a lot more lower D. And so, 1D element just has 2 nodes. Okay, so it's just simply a line segment. But we also have to define a lot more information about the beam. Okay, and so if you recall from the shells, right, one thing that we had to define for the shells was we had to know the thickness of that shell, right? So we have to define, what's the thickness that we don't see it geometrically in the geometry, but we need it for the calculations. Okay, with the beams, we have to define a similar amount of information, but instead of missing 1 dimension here, remember for a beam we're eliminating 2. Okay. And so, the important thing to remember is that, when we're using shell and beam elements, the idea is not to lose any kind of fidelity. And so we want to try to retain all of that information as possible. It's just that information might be represented in a different way. Okay. And so in beam elements, instead of defining the thickness of the beam, we instead have to define the cross-sectional shape. Okay. Okay, so let me give you an example. And so one very common beam that you would experience, especially if you work in any kind of construction type of FEA, is an I-beam. Okay? So an I-beam is a very common beam that's used in structures. Okay, and so if you were to replace this with the beam element, you would instead represent that that complex cross section as just a single line. And so in doing this, we need to store the I cross section. Okay. And so that means, storing the cross-sectional area. We would also store things like the moment of inertia. We would store things like, where the centroid is of that cross-section. Okay, so there's a lot more information that's stored kind of internally for a beam than for a shell. Because for a shell, the only additional thing you have to store is just the thickness of the shell. For the beam, there's kind of a lot more going on. So, just kind of be aware of that. And so even if you see, an FEA geometry with the beam element, just know that there's some kind of cross-sectional information that's being stored. Okay. Okay. And so let's talk about creating beams. And so creating beams is pretty simple. And so there's kind of only two methods. Okay. And so the first method for creating beams is just to simply create a 1D line or 1D sketch. Okay. And so you would just draw out the path of the beam inside your sketch, and then that will become your beam. Okay. So of course, that's not very common, because then that requires you to build the CAD model from scratch. What's more common is to take an existing CAD model and extract out the beam type geometries. Okay. Right, so method two is by far the most convenient, because then you can use an existing CAD, and then you can extract this information. And the other nice thing about method two is that it automatically stores the cross-sectional information. Okay, so let's see a question in the chat. Yeah, so the question is, how would you be able to store the cross-sectional properties if you just create the beam? No, it's a good question. And so there's actually multiple ways to do it. And so, because, there are a lot of very common beam shapes that are used in practice. And so you'll see that if you try to create one in ANSYS, that it will give you options. So these are some pre-made beam cross-sections. And so you can choose some common ones like I-beam, L-beam, circular beam, square beam, rectangular beam. And then that lets you kind of choose the properties from those. If you have kind of a unique beam that has a cross section that doesn't follow those shapes, then you can draw it. And so that's kind of the most manual way. But for most cases, I'd say 99% of cases, one of the pre-made beam cross sections will fit your needs. And so you just pick that from a list, and then you just define the properties from that. And the nice thing about method 2 here, so that's method 2 is the one that we're going to be using in the activity on Thursday. Then method 2 is just a simple point and click. And so basically you're going to look at your geometry, you're going to look and see where the beam type geometries are, and you just click on the ones, and then the process is just automatic. So beyond that, there's not much to say about beams. And so, compared to shells, they're a lot easier to, to use, and computationally, they're extremely efficient because, 1D element, at most is going to have 3 nodes if it's quadratic. And so for a 3-node, quadratic, you're getting all this accuracy, and it's really nice. Okay. And so there's a lot of geometries out there that, rely heavily on beams. So one example that I can think of here at Cal State Fullerton is the Baja team. So the Baja team, if you're unfamiliar with them, they create a vehicle, and a lot of their vehicle is made of these rods. And so for a geometry like that, and so let's say you're doing a finite element simulation of the frame, I would definitely try to do it with beams because it's going to be a lot more efficient than trying to do it with solid elements. Okay. All right, any questions on this? Okay. All right, so the last thing I want to talk about, before we end today, is to talk about accuracy and convergence for shells and beams. So we talked about it a bit earlier. We know that you generally get higher accuracy and better convergence properties if you use shell and beam elements. Okay, and that's one of the primary reasons to do it. Okay. Okay. So one way, that we've talked about before, one way that we've measured, accuracy in finite elements is how quickly you can get to an accurate solution in terms of the number of elements, right? And so the faster that you get an accurate solution with the least amount of elements, we say that that's a good thing. Okay. So we can go ahead and draw a graph here. Okay, on the x-axis of this graph, we're going to, list out the number of elements. And on the y-axis here, we're going to list the solution value. Okay. And so remember when we talked about things like the mesh convergence, we know that a mesh is well converged when the solution no longer depends on the number of elements. Okay. And so if we look at a typical curve, okay, and so we look at a typical curve, for solid elements, maybe it looks something like this. Okay. So as you increase the number of elements, the solution value is going to keep changing. It's not until you kind of reach this area right here, where the solution starts to plateau. Okay. And so when that solution starts to plateau, that's when we say that the solution has converged. Okay. If you compare this to the behavior that you generally expect for shell and beam elements, it might look something like this. And so for shell and beam elements, you can see here that we get convergence a lot faster. So that's typically what you expect. And so for cases when you can use shells and beams, and so when the geometry is thin enough or the geometry is slender enough, I would definitely recommend using shells and beams just because you're going to get a lot more, bang for your buck basically in terms of accuracy. Okay. But you have to be careful. And so, this graph here makes it seem like shell and beam elements are wonderful, and they are wonderful. I'm not trying to say that they're not, but you can only use them in the correct situations. Okay. And so in other words, you want to be careful not to try to force shells and beams into situations where they're not appropriate. Okay. Because if you kind of try to force shells and beams into kind of every situation, first of all, you're going to run into a lot of practical issues that I don't really want to get into today because we're going to deal with those on Thursday. But you're actually going to be your accuracy is going to be taking a hit too. Okay. And so generally the rule of thumb that I use is that if you can get a mesh on your geometry that has several elements through the thickness with a reasonable sized element, then just go with the solid elements. Okay. And so, let's say that you got your CAD model, you didn't really do anything to it. You load it up into ANSYS and you mesh it, and it looks pretty good, and you get at least 3 or 4 elements to the thickness. In those situations, there's really no point in trying to use shells and beams. It's just going to create more hassle for you, and you're going to get worse convergence. Okay. And so in those cases, this plot here will actually swap. Okay. Okay, and so if you look at the same plot, number of elements per versus the solution value. Okay, so this could be either a stress or deformation. And this is for thick geometries. Ones that would be perfectly fine with a solid element. And so in these cases, you get the reverse behavior. And so, for these types of geometries, you're going to get a convergence that looks like this. And this is for shells and beams versus the behavior for solid elements, would look something like that. Okay. So you want to be, kind of thoughtful about when you use this. Okay? Especially because of the other practical issues that you'll see on Thursday. So after today, kind of just judging from last year, I think after I gave this lecture, people were like, shells and beams are great. We should use them all the time. And then after we did the activity, people were like, shells and beams suck. I'm never going to use them again. And so you'll see that it's we talked about mid-surfacing. We talked about extracting beams here. It makes it sound really simple, but you'll see on Thursday that it's actually not. And so there's kind of a lot of complications that can occur. But it's kind of hard to get into it now before Thursday. So you can kind of look forward to that then. Okay. All right, and so I think that's all that I have to say for shells and beams. And so are there any final questions on this? Okay, all right, so that's all we got time for today. So thank you everyone for tuning in today. I'll see everyone on Thursday for the activity, and hope you have a good rest of your day. Hey, what's up?
I had an issue writing answers yesterday, and I finally got it to work. It was pretty much like really close to like kind of deadline or like yesterday's assignment. I managed to fix it, so if I edit my assignment.
Yeah, that's fine. Yeah, I can see it tracks whenever you have it. So I'll see that you got it on time, and then I'll upgrade it based on.
Well, I tried to get it on time, but it was like about a couple minutes, or it was a little.
I mean, if it's like 12:05 or something like that.
I don't remember. It might have been like yeah. I tried really hard. It was just like really bad time to have a computer problem.
Yeah, it happens with stuff. So don't worry.
I mean, it should have run SolidWorks and Insys all at the same
Oh
time.
yeah, you definitely should. That's tough on any computer.
Yep.
See you guys.
Yeah, thank you, Professor.
Yeah. All right, any final questions from Zoom? Or close it up. Okay. All right, so I'll see you guys on Thursday.